Okay, good afternoon. I hope you're all enjoying the conference as much as I am. Like I said, I'm Daniel Linton from Sydney Lunabotics, and we'll be representing Australia at 2013 NASA Lunabotics Competition. So I'd just like to start with a quote that summarises what the competition is about for me and for the students involved. So obviously somebody said it better than I could, and a lot earlier than I could. I hear and I forget, I see and I remember, I do and I understand. So it was Confucius, I'm sure you've heard that before. And I bring that up at the beginning because Lunabotics is essentially about education and it's about learning, and I do and I understand is what it's about for me personally and for the other members on the team. So I'm going to talk a little bit more about what NASA's Lunabotics competition is, who we are at Sydney Lunabotics, what we get out of it through experiential learning, and what we deliver to other people in the community and other students and other schools through our outreach activities. So the NASA Lunabotics competition, there's actually a couple of other speakers at this forum who were involved with the NASA Lunabotics competition. Leonard Bernold was one of the original founders, and Rob Mueller is currently the head judge. So it's an international competition. There's 50 different teams from around the world competing this year, and it's the 4th year of the competition this year. So the aim is for the students from these teams to design and build a small lunar excavation vehicle. So 1.5 meters long, 0.75 meters high, and 0.75 meters wide is your dimensions, and 80 kilograms is your maximum limit. So that's just an image of one of the conceptual Lunabot designs that we came up with. So the task of the Lunabot is to excavate as much lunar regolith as you can from a simulated lunar environment in 10 minutes. So the Lunabot starts in the start area, and you have to traverse through an obstacle area, excavate the mining area, and return to the lunar bin to deposit your regolith. There are points available for various different desirable things, such as low weight, autonomous operation, dust tolerance, and those kind of things. So this is kind of the mission statement for the competition. It's about engaging and retaining students in science, technology, engineering, and mathematics, what's commonly known as the STEM fields. So Sydney Lunabotics first formed in September of last year. We are 16 undergraduate engineering students. We come from a variety of different engineering disciplines: there's mechanical, electrical, mechatronic, aeronautical, space. We're all from the University of Sydney, and we are supported and were founded by the Australian Centre for Field Robotics, who have donated their time and their advice, and one of their academic our supervisor is Ali Gottlieb, one of their research fellows. So a large part of the Lunabotics competition is about following the NASA systems engineering approach. And while this particular diagram isn't an illustration of the NASA systems engineering approach, it's more of a generic example of the engineering approach to design. So I wanted to use this to illustrate our progress. Where we are now is at number 7, modelling and prototyping the design. We're testing, we've got a mobility prototype running, and we're performing tests with that at the moment. So we've got our complete final design. We're almost ready to start manufacturing that final design. So like I said, there's a systems engineering aspect to this competition. One of the big things that NASA encourages the teams to do is to produce a professional systems engineering paper outlining how you use the NASA systems engineering process to design your Lunabot from the very beginning of the project. So part of that is just the subsystem breakdown, which is illustrated there. So there's a picture. You can see what we've done so far with our mobility prototype and some of our software that we've developed. What's actually demonstrated there is something that we couldn't have done without the ACFR and the help of the Powerhouse Museum. We're aiming for full autonomy. No team has managed to achieve full autonomy yet, and the stakes for getting full autonomy have steadily risen over the years. So it's really there's a big motivation to get full autonomy, and we're definitely going for it. So part of that is localization, and we had somebody talk about localization without GPS, with and without GPS earlier today. So we're doing it without GPS. And the system that we've got is a visual pose estimation system. So it's actually working really well. We can localize ourselves to within a couple of centimeters just by looking at some beacons and using an array of cameras on our Lunabot. And we were able to develop this thanks to the ACFR and the Powerhouse Museum. You can see we were able to do testing here where they have and set up our beacons and use the facilities that they have there, which really helped us out. So what the team members in the Lunabotics team get out of the Lunabotics competition is an experiential learning. Experiential learning is a form of active learning where the student takes part in the learning process and works through the problems and identifies the problems for a start and works on solutions. So I've illustrated it very simply there with there's two processes basically, doing and reflecting. You can divide this into more specifics, and for instance the reflecting process should the reflecting process should I apologize. Basically, the doing means getting hands-on and actually thinking about the task in the moment. The reflecting process is standing back at the end of it, thinking about what you've done, how you could do it better, and trying to conceptualize what you've done so that you can then transfer the knowledge that you've learned from the one task to tasks that you'll do in the future. It's a vital component of education, and sometimes it's missing from university education just because it's hard to get across in through lectures and material like that. So what we're doing is a variety of experiential learning. It's called project-based learning, and it's so students run the project from the very beginning, and that way students can get a really good grasp of how a project develops and how a system develops, and that's something that's very difficult to understand without actually doing it. So we also get experience on the small level doing manufacturing design, doing manufacturing, testing, and software development as well. And as we're a reasonably small team, every member of the team gets to see how a system develops, which is an experience that is difficult to come by. And I know that is certainly the biggest thing that I will take away from this. I now can see how a project runs and how a system develops. So the doing is all those practical tasks, which is somewhat obvious in the project-based learning. You are always doing things. But the reflecting in project-based learning comes from communication with other people on the team. Obviously, it's very difficult to run a project if you don't have good communication. And what communicating does is it forces the students to think about what they have actually done and filter it down to the bare necessities, and that's a great way to reflect on your progress and what you've learned and how you can teach people from it. Another version of reflecting is thanks to our supervisor. He can reflect with us. He can show us how we could have improved what we've done, what we did, and how we can do it better in the future. Another form of reflecting is just keeping back on the edge of the Sydney Tower, courtesy of the folks at the Sydney Tower. We do get to do some fun things in this project. So we also plan to do outreach activities. Outreach activities is a part of the Lunabotics competition, and so we've got a plan to do that. We're going out to primary schools where we can introduce them to the concept of Earth mining, and obviously things have to be quite simple. So we connect it with the students' knowledge about the solar system. We try to tie it in with what they've already learned in their school, and we try to introduce an active learning component to it, a bit of experiential learning by giving them simple problem-solving activities. Asking them, what do humans need to survive, and how could we get that to them in space, getting them to draw pictures and things like that. So it's getting them into the creative side of engineering, which is a lot more accessible, obviously, than the technical side. Secondary school visits, we can go a little bit more technical. We can introduce them more to the science, and we can show them the difficulties of off-Earth mining using scenario-based exercises, which are more complicated and they can go get more involved with. But once again, we try not to have it heavily maths-based or heavily technical, because it allows more students to access it, more students to get properly involved and be interested in engineering. So part of this is, a lot of this is introducing the students to the concept of off-Earth mining, and there's obviously a lot of people out there who aren't actually familiar with off-Earth mining at all, but I've yet to find somebody who isn't interested in off-Earth mining, because it has that kind of appeal. It's an idea that has a lot of potential and people can really see that. So it's really great to see people interested and getting involved. We also do other activities. We go to the powerhouse for the testing. The testing that you saw there is all in the Mars yard of the powerhouse, which is completely open. Anybody can approach and watch us testing, ask us what's going on. We've also been there as a team and set up. We also plan on doing public seminars and seminars for students, undergraduate students, and all kinds of students at universities. We also have website content, learning content, our blog where we update our progress and details on our Lunabot design and why we've chosen that design and how we're working through it. So we also recognize the potential to do research through this project. So what you see here is testing we just did the other day, and it's on the beach. And for those of you who are familiar with the lunar regolith simulant that you've seen around, sand is not an ideal simulant for it. So that's why we're going to build a full-size lunar arena to test in, which will be filled with exactly the same regolith simulant that you saw out there. So it's going to be interesting. You can see we've performed some preliminary tests with different kinds of wheels and the working out the traversability. It'll be really interesting to get involved with the actual lunar simulant and be able to do some experimentation there. There's also research that we want to do with the power, regarding the power subsystem, and the autonomy side of it as well. So, looking towards the future, the competition is in May, and we hope to send as many of the team over there as possible. There's some images there from last year's competition, and we want to continue to provide project-based learning experience, research opportunities, and outreach through Lunabotics and other competitions like it. So we're not just limiting ourselves to Lunabotics, though we do want to stick with Lunabotics. We've all learned an incredible amount from this already, and we're very excited about what we can do in the future. So I'd just like to thank the ACFR and the University of Sydney for their support, the ACSER for hosting us here today and giving us this opportunity to talk, and our diamond sponsors, the ACFR and Maytech. We are looking for more sponsors, so if you are interested in supporting this project in any way, please come and talk to me. We really appreciate it. So you can find out more on our website, we have a Facebook page, or you can contact us on those numbers. So I have raced through that presentation because it's amazing what a bit of adrenaline can do to you. So are there any questions that anybody has?
What's your budget, Andy?
Our budget, we started off with $10,000. We are expecting to have non-monetary, for instance, Maytech, our donor sponsors, sponsored us in kind. So
That's the message, right?
yeah, that's the message. Absolutely, we accept any kind of donation, any kind of in-kind donations are excellent as well.
Food?
We do accept food. Yes.
You mentioned that you want to build an arena here in Sydney to
Yes,
capture
it will be in Parramatta. It'll be 7.4 metres by 3 points. So it's decent size. It'll be filled with several tons of regolith.
What's in one?
The same simulant that you see sitting out there on the table, it's the crusher dust from a quarry up in Colorado.
Okay, very good. Good luck.
Thank you.
Hi, quick legal question. Who's going to own the intellectual property in all the discoveries?
That would be the ACFR.
And actually, as far as I know, luckily I'm not a lawyer, but sorry for. As far as I know, what students actually invent in practice belongs to students. So although we are as an ACFR supporting them, so if they invent something, it belongs to students, not university.
So NASA doesn't want to own what you produce?
They haven't asked to own it. But if they wanted to own it, I'd be more than willing to.
You're making very wealthy one day.
Well, you got a construct before, right?
Yeah, just quick. What's past record of total amount in mass for 15 years last few years?
Well, the rules have changed over the last couple of years. People have reduced in mass, and the key thing that has come out is that it's the ratio between the mass of the Lunabot and the mass of the regolith that you can collect. So that's actually the key figure, really. But previous teams have mined 200 plus kilograms. But they were with much bigger machines. With machines similar to our size, between 50 and 100 kilograms is a really good result. Yeah.
So that's your sort of current performance.
Yeah, absolutely. Yeah. Yes.
So I don't need technical questions about the thing, but how far are you required to move any regolith that you mine?
We have to take it from the mining area back to the depositing area, which is a maximum. It's the whole arena is 7.4 meters long. But along the way, you have to, navigate around obstacles and that kind of thing. Anybody else? Yes.
How dense are the obstacles that you have to navigate around? Are there any specifications that they give you on, like what?
Yeah. So the maximum size of the rocks, they're just rocks that you have to navigate around. There's 3 rocks with the maximum diameter of 30 centimeters. There's also 2 craters with a maximum diameter of 30 centimeters. Yeah.
Thank you, Daniel.